This is a video that is going to be corresponding to lesson two. Um, just wait one second, make sure I have the right one. Yeah, lesson two, where we're going to start talking about the. It's kind of working our way up to the quantum mechanical model. So we're going to talk about Bohr's model. So Bohr's model. It only works really for hydrogen. Bohr did a whole bunch of like calculating and things that confirmed his model, but it only worked for hydrogen. But parts of Bohr's model are still true today, and one of them is just talking about ground state and excited state. So ground state is when the electron is as close as possible to the nucleus because it has less energy. And then excited state is when the electron has absorbed some energy and moved to any higher energy level. And then we talked about this with the lab, but absorption is when the electron becomes excited. It would move from here and then out here. And then emission is when the electron then returns back to a lower or ground state. So Bohr is, thought about the atom as being kind of like the electrons were orbiting, like planets would orbit the sun. And he labeled those orbits, n equals 1, n equals 2, n equals 3, and so on. And that level of each orbit is called the quantum number. So you can see in this table that, mainly this is the part, but the radius is getting bigger as you get to the higher n values. And then, not that you need to know, but you probably noticed when you did the POGO, the spacing and energy between the levels isn't equal. So this isn't really a linear relationship as you there's bigger spaces for some and smaller for other between energy levels. This is kind of tied to the lab and the POGO. So you can see, the electron in a hydrogen, when it's in ground state, it would be at n equals 1. But the transitions that we saw when we did the line spectrum lab and with the POGO is always going to go to n equals 2. So the electron had to have been excited and then come back to 2 for us to see it. But there's other times where the electron doesn't go back to the second n equals 2, but here they'll go back to n equals 1. And these are all in the ultraviolet region, so we can't see this. This has, more energy difference than any of the visible colors that we can see. And then the infrared part of the hydrogen electron spectrum is the electrons don't go back to 2 like they do for our visible, and they don't go back to 1 like the UV, but they do go back to 3. So these are going to have less energy than red, and we're unable to see them. So let's do an example here. This is very similar to what you did in the lab, but I want to go over it with you. So this is looking at two different photons that have different wavelengths. So the photon up above, the 560 versus the 675 nanometer photon. So the first photon is going to actually have more energy and correspond to a higher frequency wave. And the second photon is, because the wavelength is bigger, it's going to correspond to a less energetic wave. So if we put the electron for the, let's say the visible part, n equals 2, so it's already absorbed some energy, the photon, it has to be the exact right photon. So some photons will do nothing. But if it's the right photon, the electron will absorb it, and then it'll move to a higher level. And it, how it temporarily kind of stays out here, and then it comes back down to a different lower level. And when it does, it gives a color sometimes that we can see, or it gives back, energy in the UV or the infrared, like we were just talking about. So I don't really care that you know the exact transition, that you know exactly what color that is. I'm not going to ask you to memorize that. But what I do want you to know is like this second nanometer photon here, it has less energy. So if I take an electron, like let's put it at n equals 2 again, and that let's assume that photon, that the electron absorbs the energy, it's not going to go as far. So you could draw it going just to n equals 3 or just something less than the previous one. So I'm going to draw it here going not as far because it didn't absorb as much energy. And then I'm going to show that it returns back. And when it does, let's assume this is a color we can see, and it would have a bigger wavelength. So Bohr, like I was saying earlier, it doesn't work for anything other than hydrogen. So other elements, they really tried, but the model didn't work. So that led us to starting to look at the electron differently. So de Broglie is the first person that kind of said, well, Bohr's kind of right. They do have these certain energy levels, but maybe the electron isn't a particle, but it's acting as a wave. So just like light is both a wave and made up of particles called photons, electrons are also particles that can behave as waves. And then, so de Broglie was the first person then to look at if they're in a specific wavelength, if they're acting as a wave, then that would correspond to these fixed radius orbits. So I don't know if you've ever seen a standing wave, but I do this with my dog's leash sometimes. Like I'll jiggle it up and down. Sometimes as I'm doing it, like let's say I have a tree and I have like a rope attached. Sometimes I do it and it's just kind of random. But after you get it going just right, you end up with something called a standing wave, where the wave is still moving, but it almost looks like it's not. So the crests and the troughs are always in the same spot. So, when you're moving the rope or whatever, it keeps kind of going back exactly where it was. So those are standing waves, and they're only at specific wavelengths. Then that would then correspond, if you look at this diagram, to different radii of the energy levels. So de Broglie was trying to, link Bohr's model and still use that, the n equals energy levels of the atom. This is the equation for de Broglie. You don't need to use it. We're not going to do the math this time, but I think it's kind of interesting because if electrons are waves, and can be thought of as waves, so are we, so are cars, so are jet planes. But here's the deal. This is mass and this is wavelength. So they're inversely related. So if you have a person or a car or a plane or a train, they have a really large mass, which makes this really little, like approaching zero. So the wavelength of things like us are so small that it's not noticeable. This is really only noticeable when we talk about particles that are small, like electrons. One more thing is the Heisenberg uncertainty principle. This is just stating that you can't know precisely where something is and its velocity at the same time. So really, it's kind of talking about the electron. If you try to observe the electron with light and photons, it'll move the electron's position or change its velocity. You can't know both at the same time. So that means that we can't talk about electrons being specifically these little planet-like, going around in a circle. We don't know that because we can't know where they're at. An analogy to this is if you were to go bowling in a completely dark bowling alley, and you're in the alley and you have the ball, there's pins down in the lane, and then you throw it and you hear them. So, oh yeah, they were there, but then they're not there. They moved all over. So it's somewhat similar to that. So we can't know for certain where an electron is. That's where we kind of leave off with Heisenberg.